All right, this is the first real video of this course, so the first lecture, and it's going to be a relatively, in some sense, maybe light lesson compared to the future, because we are going to probably revise parts of computer architecture. I'll redo the sort of the old story from the very beginning, so that you bring back to memory things that hopefully you know already, or if you discover that you don't know, you have the opportunity to go and read appropriate books and references to make sure that you are up to speed. It's very important that you get up to speed quickly, because otherwise when we move to more important chapters of this course, you may have problems to follow with that. One of the pity of this situation is that this is a course and is a part that I usually enjoy very much to do in a very interactive way, basically trying to visit everything with your help, with some interactivity, which of course we cannot have now. And unfortunately, that also helps me usually get a feeling of the level of the class, and I will get zero feeling today, probably. You'll figure out with time that I do fairly often, every now and then, some pauses in the videos asking you questions and inviting you to answer those questions. Please do consider really stopping the video in those places and figuring out by yourself the answer. I think it's a very useful exercise and is a way for you to check that you're not just passively listening to my blubbering, and is actually you are absorbing some of the content, understanding some of the potentialities of what we are doing. I may be doing a little bit more even today, maybe not really stopping the video or doing the real pause, but I will be asking a lot of rhetorical questions, saying what we do now and so on and so forth. Also here, it may be a bit annoying, again, this should be very interactive, but do consider the possibility of stopping if you're not completely clear about things, and maybe going and reading or thinking a bit to these aspects. I think it will make this revision, because essentially what we do today is a revision, will make this revision more efficient. Okay, let's start. So the first part of our Advanced Computer Architecture course is on general purpose architectures, essentially how the processors that we use every day in our laptops, through the cloud, in servers, and in our smartphones, they are all essentially built the same way. We look at how they work. And this section of the first part on general purpose computing is called Exploiting ILP Dynamically. If you don't know what ILP is, you'll discover it in a few seconds. So this is the traditional way to exploit instruction level parallelism. That is to try to make machines, try to make computer fast by overlapping the execution of different instructions. Our programs are essentially sequential programs. We have sequences of instructions, and we will try to do something on these instructions to execute as many as possible in parallel, and therefore complete the task faster. So there is a joke that I always say on this slide, is that in computer architecture there are three goals for in the optimization of a system, right? And I think the first you can guess, it's speed, right? The first goal is we want to make it fast. And then the question is, what are the second and the third? And my joke is, well, the second is speed and the third is speed. That is, it has been an overwhelming importance in microarchitecture design, the fact that we make our machines go fast. even in 2021, with the importance of energy in the picture, I think one can still say that the purpose and the optimization is speed. Energy is essentially a constraint. It is a constraint in our laptop. It is a constraint into our smartphone. It is a constraint, of course, also in the data center that is using a large fraction now of the energy on Earth. So reducing energy is important, but it's not the primary optimization goal. It's sort of more the constraints. I get an envelope of energy that I can consume, and the purpose is to go as fast as possible within this envelope. This is the story of computer architecture, which is essentially the story of gaining performance. If you look at the last few years, it's becoming a little bit sad because we don't see the same advantages and the same progress that we had before. But what we will concentrate upon in this course is maybe the most glorious years, the end of the past millennium, where the performance gains were tremendous thanks to two things that were going particularly well. One was technology, nothing to do with this course. There are our electrical engineer colleagues and maybe even more our physicist colleagues that have been doing a tremendous job in doing transistors smaller and smaller, faster and faster. And actually the two things go together because the smaller they are, the least parasitic capacitances and resistance there is, and so naturally they will go faster. That is a large part of the progress in the past and is essentially one of the most important explanations of why things are flattening out is because, again, technology is not keeping up. You have maybe heard the end of Moore expression is that there is this law or empirical observation made by one of the founders of Intel that density will grow at an exponential rate, and well, density is not growing. It is not a law. It's an empirical or maybe an economical actually observation of what economy manages to push physicists to do. But now physics can be controlled only to an extent, and we are to the point that maybe we will not manage in a few more years to squeeze transistors anymore and to get transistors that are faster than the previous generation. So technology is disappearing, but it didn't explain, even when technology was improving fantastically, it didn't explain the 50% year improvement. Part of it, let's say roughly half of it, is essentially due to improvements to the architecture. And this is exactly the topic that we will see for maybe the first third of this course. It's probably a bit more than a third in practice. Maybe it's interesting to have a look also to the to what happens of clock rate. Clock rate is not speed, right? Clock rate is only the frequency at which my circuit operates, but it depends on how many instructions I am executing in a given clock cycle, how many cycles it takes to execute a specific instruction, and so on and so forth. So there are a number of things that make clock rate not particularly telling. In fact, maybe you are a little too young to know, but there was a time that Intel was basically advertising to the consumer their processors based on the number of gigahertz of the clock rate. And it was a very misleading representation of performance because it didn't mean necessarily that Intel processors will be faster because they were operating at a higher clock rate than other processors on the market, but it was a number that was very easy to present. And then at some point, it basically flattened. As you can see, there have been very little progress from the turn of the century or turn of the millennium until today. It has some correlation, though, with technology, right? It's the moment that something started not to work, at least not as well as before in technology, and it worked very well in the meantime. Also, clock rate doesn't mean only technology. Clock rate improving, and the 40% per year in the golden era at the middle of this diagram is essentially also linked also to the pipelining, to improved pipelining, to improved ways of creating the silicon. So what is architecture doing to make things faster? The job is specified, right? We need to execute a program that is made of instructions, and these instructions to a large extent are fixed. So what can we do? One of the things that we can do, and the one that we are interested in, is to exploit parallelism. Actually, maybe every sort of speed improvement somehow, architectural speed improvement somehow comes from parallelism. But the type of parallelism that we are interested in this course is instruction level parallelism. And as I said before, it's essentially the idea of trying to execute in parallel some of the instructions that were given to us sequentially, because that's the nature of the program, and therefore run faster. We will see, and it's the sort of the second section of this chapter of this course, VLIW and EPIC, other techniques to extract this parallelism and actually to get this parallelism directly into the hardware already specified. It will be much more clear a bit down. For now, we'll look into these ideas of pipelining and superscalar. So we are going to go back to the very beginning of history, not finally so long ago. Maybe a classic processor in the 70s, 80s will be exactly executing like we see here, right? Over time, over the different cycles, we will execute the different instructions, and we will take a number of cycles for each of the instructions. It is the model that even as a programmer probably you have of the execution of a program. So we can ask ourselves a few questions about this, as just to bring back to memory the basic things, right? One question is, for instance, I notice here that there is one instruction that takes 5 cycles, one instruction that takes 4 cycles, and so on and so forth, right? It's very easy to imagine that there are instructions that are very, very simple. I don't know, the simplest instruction is probably the one, the simplest meaningful instruction is the one that copies a value from one register to the other. It's not very useful computationally, but it's certainly something that I need to do from now and then, and it's a very simple instruction. I may have instructions that do a trigonometric function in floating point at very high precision, and probably it will take some time more to do it, right? So one of the questions is it easy in this kind of processor to have different length of execution? So instructions like in the example that do 5 and that do 2, or instructions more dramatically that do 4 or do 50 cycles to execute a very difficult instruction. Okay, to answer this question, maybe it's good to remind ourselves how a processor like this will be done, right? It will be done as a set of functional units that do the different things that I need to do, a register to keep the register values, an adder to do additions, an ALU to do all the operation, a floating point unit if I need to do floating point operations, and so on and so forth. And there will be someone, some controller that manages all these components and the interconnectivity between them. So typically there is this controller that has a simple form of a finite state machine. So how is this finite state machine done? Well, essentially I have a few states which start from a state where I go into memory and I read my instruction, we usually call it fetch, to a state where some probably combinational logic looks into this instruction that I just brought in and tries to decode, that is, understand what else needs to be done. And there, depending on what this instruction is, the next state can be completely different, right? Now I could have some state where I do the copy between one register and another one. It's an execution phase of a very simple instruction, which ends up in maybe doing a write back in a register and saving the result. Or maybe I need to do something very complicated. I have to spend a number of cycles in a floating point unit to compute something that is extremely complicated. I will get better in drawing with time. I hope you have some patience on the board, will be easier. What might happen is actually that even I have some algorithm in the computation where I need to continue the computation several times and remain into some state until, for instance, some residual in an arithmetic computation is gone to zero. And so the number of cycles for each instruction can be completely different depending on the actual instruction that I am executing. I may be executing this instruction and it will take 4 cycles. I may be executing this instruction that through a few loops into this will take another number of cycles. Okay? I hope you have in mind, present in your mind, the machine, how it could be and how it could look and how it could be built, because this is a starting point, right? And it's an important starting point. Again, it's not a ridiculous machine today. It seems a very trivial machine, but this is how many machines were built in the past. And you will see much later in the course that today we tend to do, in some cases, hardware still following this kind of structure, right? All right. So this is all good. Where can I go with this? It's the first step in the history. At some point, people realized that they would like to do something else, something better. I ask you the question, what is the next step? It's a word that I used already a few times in the introduction today, that you probably should know, is the idea of pipelining, right? It is the first time that we are going to do something with parallelism. We'll see how this figure comes about exactly, but now, before we have done executing the different cycles of one instruction here, the 5 cycles called fetch, decode, execute, memory, and write back of this instruction, we start already, before we finished, start already executing something else. It is not necessarily something that everybody calls instruction level parallelism. It's still not really doing things completely at the same time, but clearly there is something that now is done at the same time, and therefore we expect to go faster. What is the image of pipeline that hopefully you have in mind? It is this one, right? And maybe you have a different figure almost 98% of the students and maybe of the people in the world that know what a pipeline is think of a 5-stage pipeline like it was the one of MIPS. It doesn't need to be 5-stage. It was a chance of technology at the time that it was on 5 stages in particular. But this is the classic image. Maybe we do a little sort of break before continuing looking at and understanding this figure to understand a bit more in general what pipelining is. So let's try to take a piece of paper, so to speak, and have an idea of what pipelining is. Pipelining is not something that has per se to do with processors. Of course, we are interested in using it in the context of processors, but it's something that we can use for absolutely any digital circuit. So one way of looking at it is to say, okay, there is here a circuit, a cloud of logic, of combinational logic, with some inputs and some outputs, and we want to pipeline it. First of all, what is a combinational circuit? I hope everybody is clear, but let me repeat it for safety. A combinational circuit is a circuit whose outputs, so what I see here at the output, depends exclusively on what is present in this moment at the input, right? So it's a circuit that doesn't have memory, or in other words, it doesn't have, for instance, a D flip-flop, data flip-flops, right? So there are only gates in here, right? There are only logic gates of some nature, or if you want, I could also think of it done of more complex components like adders, multipliers, and so on. It doesn't matter, of course, the adders will all in turn be done in gates, in logic gates, but it doesn't matter what I'm thinking of this circuit. Now, the first question maybe is how fast can I run this circuit? What limits this circuit to run faster? Maybe you want to, is one of those cases where you want to pause a bit the video to make sure that you have an idea of what limits, right? There are physical limits that prevent us from operating this circuit at sort of, let's say, an infinite frequency. We need to wait some time. Why? We need to wait because there is a notion that is important here, which is the critical path. It's something that is extremely important for everything that we will do in our in this course, and we do in architecture, is the fact that something limits our speed. There is a speed at which signals travel through our circuit. So if I want to go from here and I change from 0 to 1 this input, it will take time before the value, I don't know, the exit 1 goes into a 0, for instance, here. So there are paths through this graph. This is nothing else. A circuit is nothing else than a graph of gates or of other components. Each path has a time associated with it, a propagation time associated with it. And the worst of this timing, the longest of this path, which is called the critical path, is what limits the speed. I cannot operate this circuit at a higher speed than the time that it takes to propagate through the circuit, otherwise I will capture a wrong value. Why is that? I mean, if it is not clear, imagine that you have here a register and here another register. So essentially this is a set of D flip-flops. I hope again that you remember what the D flip-flops are. They are a very sort of strange component that on a raising edge, or one edge, but typically a raising edge would copy what is at the inputs and show it at the output and keep it at the output until the next raising edge. So first of all, it's a memory element, is a non-combinational component, and it has this peculiarity to basically show this value on the raising edge here. And as it shows a new value, it's like this transition, right? Maybe this pin goes from 0 to 1, then it propagates. And if this is the same signal, clock signal, and it transitions after the clock, this T clock must be long enough for the change in value at the output of my circuit to be there, because otherwise what I copy to the output here, to the rest of the circuit, will be not the value that I expect from this function. Of course, this is whatever, right? This could be a divider, right? And has got a new operand here, and it must capture the result of the division in the next register. Very good. So the critical path is what determines the operating frequency of our circuit. Maybe we can stop for a second to ask a different question or a related question, why there is in a circuit a propagation time. Why it takes time, if I redraw a little bit of my circuit, why does it take some time to go from the input to the output? Again, it's a question that I would like to ask you in person. Try to think of it, and it may be that some of you, especially the non-electrical engineers, I know that in the class there are a number of electrical engineers and a number of computer scientists, maybe the non-electrical engineers will give you the wrong answer. It's not a silly answer, but it's not the correct one. One of the answers that one could say is there is the electrons move at most at the speed of light, right? So there will need some time for an electron to go here, or vice versa, depending on where how the current is going. This is not a wrong answer. It's simply that our circuits go much slower than speed of light would allow. This is one of the reasons why a lot of people are trying to do computers with photonics instead with electronics, because the hope is that in that case we will be operating at the speed of light. In our case, no, we have something else. So I'm going to draw one circuit for the sake of it, because I think it's useful culturally for all those that also don't know. This is the simplest circuit that we can do with transistors, and I hope you are clear on my audible writing. This is a transistor. What are these transistors? They are essentially switches, right? And this is called an inverter because if this is 1 and this is 0, these two are actually opposite types of inverters. In fact, people put typically a little round here to make sure that one understands. How do they operate? This is a switch that when there is 1, it's open. So if here there is 1, this is open, there is no, it doesn't conduce electricity. This is a switch that when there is 1 is closed. So this is actually acting as a wire. And so what happens is that basically this node at the exit is not connected to the 1, but is connected to the 0, and the result is 0. If I had here, instead of the 0, of the 1 a 0, I would have the exact opposite situation. Here, I would have a connection. Here, I would be broken, and the output will be connected to 1. So this is a component made of 2 transistors that brings from a 0 gives out a 1, from a 1 gives out a 0. I hope everybody is very familiar with this component. It is this component here, which is called an invert. Okay, this is not the reason we are here, but we needed to have a circuit to play around. So let's delete a few of these things and come back to our main question, which was why my circuit needs time to operate. Why this circuit, when I change from a 0 to a 1, my input value, let me take back, when I go from a 0 to a 1, so this was at 1, why does it take time to go to 0? And again, the reason is not a problem of propagation. The problem here is that this node has intrinsically a capacitance. There is a capacitance to Earth that is charged. The moment I have a 1 here, this capacitance is charged. The moment this transistor closes and this transistor opens, it tries to discharge this capacitance through the transistor. And now if you know a little bit of physics, right, you have this kind of curve. You have the voltage at the around this capacitor that goes down. And this takes time. We will feel this as a 0 when it will be less than half the voltage of a 1. So it will take some time, which is here, to get to a point that I say, oh, before I thought it was a 0, now is a, I thought it was a 1, now it's a 0. This time here is the time that it takes to go through my inverter. Okay? So the time, the propagation time through a circuit is essentially due to the fact that my circuits are real physical components, and that physical components have characteristics like capacitance that are non-zero, non-ideal, despite the fact that I try to make this capacitance as small as possible, but it's non-zero. And because it is non-zero, I have a delay. The smaller I can do this capacitance, the faster will be my circuit, which explains one of the things that I said before when I said that with newer technologies, typically I go also faster. It's not only smaller, but it's also faster, and the two things go together. Sure, because if I do a smaller transistor, I do also the smaller capacitor that is embedded into it, and this capacitor being smaller, typically it will be faster. Okay, but let's go now back to our pipeline, to our circuit, combinational circuit with these two registers on the two sides that has a specific critical path, so some length of critical path. and therefore can operate at maximum at some frequency. This is the performance that we can obtain from this circuit. So what is this idea of pipelining? The idea of pipelining is to cut this graph, to make a cut of the graph in pieces, such that the critical path of this part is, let's say in this example, 1/3 of the critical path of the or 1/3 here, and 1/3 here. And while I do this, when I do this, then after I've done this cut, I put here a register, much like the one that is at the input and the one that is at the output. Okay? So what has changed in my circuit? The first thing that has not changed is the functionality, right? Whatever I was computing, I am still computing. It's relatively easy to convince yourself if it is not self-evident, because I have these values that were all at the same time here, and now I'm just capturing them into a register. Then I send them in the second stage, and I capture them here, and so on. And so what I eventually will get here in this register is exactly the same thing that I was getting at the beginning. What else has changed? What has changed is that before, my constraint in the operation of the circuit was the length of this path was Tc, so the maximum frequency would have been 1/Tc. Now the critical path, the longest path between two registers, is 1/3 of Tc. So now I can operate the circuit at 1/1/3 of Tc, which is, of course, 3 times the frequency original, right? Let's call this the original frequency. Okay, so this is an important change. I can now operate my circuit 3 times faster. So my clock frequency, for instance, has gone up. Is that good? A priori, not much has changed, right? Because I do a cycle faster, but I will need to get 1, 2, and 3 cycles to get my result. So the time that it takes to get my result is exactly the same. I have just a clock that is faster, but it doesn't mean that I get my result faster. So the speed, the operating speed of the circuit is better, but the performance of the circuit is exactly the same. Or not. Not completely, because there is something else that now I can do and I could not do before. What I can do is that when I am computing something in this part of the circuit, now this part of the circuit is doing nothing, right? Nothing, because there is this register that acts as a barrier. Is a memory, is showing me the past result of the section of the circuit to the left, and therefore it isolates basically the two parts. But then now that it is isolated, I can do something else here, completely else, another operation. So suppose that my circuit is, I said before, a divider. And suppose that I have a lot of divisions to do. If I have only one division, this circuit is completely useless, this modification that I made of the circuit. But if I have multiple divisions to do, while I am doing one division here, I can already do another division here and yet a third division in this part of the circuit. Okay, now what is happening? What is happening is that the latency to get a result, that is the time that it takes from the moment the operands of a division are here and the result arrives here, is ideally not changed. I'm going 3 times faster, but I need 3 cycles to get to the result. So altogether, nothing has improved. But now, how often do I get a new result? Or how often I can start a new computation? And this is where I gain. Because before, I could start a new computation every TC. Now I can start a new computation every third of TC. So 3 times faster. And this is what I gain. Right? So this is the idea of pipelining, is that lambda, the latency will not change, the throughput will instead be multiplied by a factor, and the factor is ideally n, the number of stages I have carved out of my original circuit. Let me show you from my slides of the bachelor course a couple of animations that maybe help understanding what is happening. And here is the animation. Let's start with the combinational circuit, right? Essentially what happens is that as time goes by, different transistors get activated, basically change in the way that we have seen our inverter, the 2 transistors of our inverter, change, conduce electricity, and change the value of a node at their exit. And this propagates through the complete circuit. When we add registers in between, within each section of my circuit between 2 registers, what happens is essentially the same. But over the complete circuit, I have now control on what advances where. Now, if you compare this little animation with the previous one, you see essentially the point of the latency being equal. It's not going to go faster to the end. If it takes some time to arrive to the end, now it will take the same time, except that I do control the advance, but I cannot make it advance faster than it was advancing before. And the third animation that I want to show is the one that takes advantage of this separation by saying the moment my first operation goes in the second stage, I put a new operation in the first stage. And then when these 2 progress, I start a new operation. And so on. Now, if you look at how long it takes to one of these colors, to one of these operations to go from left to right, it takes exactly the same time as before. The difference is that once my pipeline is full, full means that there are operations all over, what happens is that every cycle, I have one new operation arriving to the end, to the right. And this is exactly this notion of pipeline, right? Pipeline in the sense that you introduce things from one side, you don't know what happens in the middle, but then at some point, this quantity thing that you put on the input will come out as a result from the other side. Good. I hope this helps you visualize a little bit what this pipeline is. Okay, so if we understand what this pipelining is now, let's try to understand also what are the limits and what are the non-idealities compared to what we have seen. The first thing that is a little strange is that we have this circuit, right? We have these registers, we cut it into a number of parts, and the result is that we are now ideally going at a frequency that is 1/n of the original one. That is, I have multiplied the throughput by a factor n and kept the latency unmodified. Isn't there something strange? Isn't there something that already stinks? Of course, the first thing that you have to notice is that you say, okay, but so if I can change my my throughput by a factor n, let's take n extremely high. Let's make n, I don't know, 1,000, 1 million, right? And therefore I will be incredibly faster in terms of throughput, which is probably what I care, at least in some problems. This tells you a little bit what maybe Intel used to do at some point, right? The game of showing a high speed doesn't mean necessarily that that we really manage. Why don't we manage? What goes wrong if n is very large? Well, it's the difference between an ideal pipeline where I think everything is perfect and reality. What is reality? Reality is that the moment I start adding here some registers, these registers add a delay. So the fraction that I have of these TIs, right, these different parts I cut, I have to add to this something that didn't exist originally in my circuit, which is the delay of the flip-flops. Okay, so this is one reason, right? I put new components in my circuit, and these components are by themselves non-ideal. What else goes wrong compared to the reality? You have a sort of silly example on this slide, is the fact that I need to cut in 3, and maybe I cannot cut my circuit perfectly in 3 equal parts. In the silly example is because I have adders and subtractors, and there are 5, so I cannot divide 5 by 3, so I can only do groups of 2, and 1 is unequal. Now, what is my critical path is the longest of these paths, so it's the maximum across all the TIs plus TFF, and therefore my throughput and my latency have grown not by this factor n, but corrected by these two phenomena. My cycle time will not be as good as it could have been, not 1n, because of these two phenomena. So the latency will actually increase, right? Because now here, even if I forget the flip-flops, right? I need 3 cycles, but now these cycles are 2/5 of what I had at the beginning, and so I need 6/5 to arrive to the exit, so I have, 20% more time. So my latency has actually gone up. You see it written here, right? The latency of the pipeline is always worse than the latency of the original circuit. So it should be identical, but in practice it's not going to happen. And the throughput will grow less, and it will grow less and less for larger n's, because the two phenomena will become worse. TFF, which is a fixed value, will dominate at some point over TI, so it will make no sense to cut further, and the inequality of the cutting will increase the more is shallow what I'm cutting, right? The least components there are to cut, because I want to cut very often, the least possible will be to cut in a quasi-ideal way. Okay, so this explains something about why pipelining is not as ideal as we say, but it's still very good, right? It means that for an N that is probably relatively small, a few units, I still can get an extremely good behavior. So it's a very good idea. Maybe before going away from this image and coming back to our processor, one of the natural questions is to say, okay, what is the price for all that? Does it cost something to do pipelining? I gain over a few fronts. Maybe I already said that there is one loss, is that latency has gone down. Maybe I care, maybe I don't, right? But maybe I do care. Is there anything else that is a price to pay for this? And I think there are two aspects that come almost immediately to mind. The first thing is that it costs hardware, it costs transistors, right? I have to add these flip-flops, and these flip-flops are resources, area, transistors, cost, right? This cost may be important, right? Maybe my circuit is a very fat circuit. It's something that starts from a few inputs and ends into a few outputs, but has a very large, very fat graph inside. Think of a multiplier. If you remember how a multiplier is constructed, and if you don't remember, you can stop the video and think for a second. The multiplier has a lot of internal signals because it has to generate all the partial products. So if I start and decide to cut this multiplier and put flip-flops in the middle, maybe I find myself with a huge number of flip-flops that has little to do with the ones at the beginning and the end. It's more quadratic to the number at the beginning of the end, and so it's really bad. So there is area, there is a cost, but okay, transistors become smaller and smaller, so maybe they are free in some sense. What else is a disadvantage? Another disadvantage is that whenever you put area, you put transistors. If these transistors are active, they will consume energy. Maybe I want to spend a few seconds to remind everybody where energy goes in our circuits. So let me take again, a piece of, so to speak, paper, and let's try to draw again a little circuit, which maybe is the same as before, so that it's easier. So here is again our inverter. Why this inverter consumes energy? So this inverter and this way of doing circuits with these transistors used as switches, as controlled switches, is called CMOS, which almost certainly all of you that are from electrical engineering know extremely well as a technique to create circuits, digital circuits especially, and maybe people in computer science maybe have heard almost per chance this. It's a specific way of doing circuits because it's the C, it doesn't matter too much what the abbreviation stands for, but this C means complementary. And it's complementary in a very much computer science sense because there is this part of the graph and this part of the graph that do exactly the opposite. When one of the two is open, the other is closed. In this case, a trivial case of the inverter is absolutely trivial. It will be a bit more complicated in more complex circuits. Here we have two transistors, and when one is open, the other is closed, and vice versa. So the idea is that we do all our circuits, all our processors with circuits done exactly in this way. It's either the top path that closes and connects the one to the output, or alternatively, it's closed the circuit at the bottom and connects the 0 to the out. And this is how I get the 0 and the 1. So the first observation, which is quite important to understand, even for architects, is that the technology that we're using for doing circuits, in a first order of analysis, consumes nothing when it's not operating. Right? I hope it is clear to everyone based on simple original physics. There is no path that goes from the plus to the minus of my battery, right? So there is no current that goes anywhere. So what we say is that the static energy, the static power that is consumed by my circuit is, again, in a first order of analysis, 0. If these switches are perfect, is 0. So this is one of the important properties of CMOS. So CMOS was actually a terrible technology initially, but what launched it, and it's good to say it here in Switzerland, although it was a bad thing for Switzerland that was doing mechanical watches, it was used for watches. The Japanese started using it to do watches that would last extremely long on the battery. And why would they last extremely long for a battery? Because in a watch, what happens is not so much, right? Maybe every second or maybe every fraction of a second, I need to count time, right? I need to change something. But in between, nothing happens, and my CMOS circuit consumes nothing. So when does my CMOS circuit consumes? It consumes only in the transitions, and it consumes only because of the same. Sorry, I need to convince this guy. Because of the same parasitic capacitance, that I have here. What happens? If I have here a 0, it's not important, then if there is a 0, this one is connected, and this one is disconnected. And what happened of my capacitance? My capacitance is charged to the level 1, right? Or speaking in voltage, if this is called VDD, there is a VDD at this, across the armatures of the capacitance. The moment I change, and that's it, right? There is no consumption. But the consumption starts the moment I have the 0 that becomes a 1. This is now closed, this is open, and I have to discharge the capacitance. Discharge the capacitance means that I take some charge from here, and I bring it back here. Now, if I continue to switch this input from 0 to 1 to 0 to 1, what happens is that I'm bringing charge from here to the capacitors, and then the next transition, the charge back to the 0. Then again, some charge to the capacitance, then back to 0. And therefore, over time, I am in fact transferring charge from plus to minus, which requires energy, and which means that I am consuming energy. So the consumption of the of my CMOS circuits, it's first of all due to my parasitic capacitances that I have in my circuit, and acts, as we said, only during transitions. If there are no transitions, in the first level of analysis, there is no dynamic power that is consumed, and nothing is consumed. So the point is that if I put plenty of registers now, plenty of D flip-flops, cutting my circuit in very many places, and I want to cut as much as possible to increase my throughput, right? We said it. Then I get much more power consumption, energy consumption. So I have to be per cap. So this is one of the costs. All right, so let's go back to our processor. So here is our processor. How we want to do it as a pipeline processor. I think it's immediately relatively clear that it resembles what we have done of our previous circuit, right? What we have here in these dark blue bars that are here are essentially the registers, are the D flip-flops that we had introduced before, and what is in between is combinational logic that in this case has a very specific functionality that we can easily guess by the usual initials. We are fetching an instruction, we are decoding an instruction, we are executing whatever it means, an instruction, and so on and so forth, until we write back the result of an instruction. So what we have is that we have taken our instruction that was in fact somehow already split into pieces, and we have put these registers in between to build essentially the same thing that we were doing for the arbitrary zero. We were saying before that a pipeline helps not in latency, not in getting a single result out, but in throughput, in the number of results that is capable of computing per unit of time. Let's look if it is useful for our processor in a first, at least level of analysis is perfect, right? Because we don't care so much if one of our instruction takes 1 nanosecond or 1.5 nanoseconds or whatever else. So what we care is that our billion of instructions that we need to execute for in our program, what cares is that they execute as fast as possible. So the throughput of the instructions is what matters. So it's perfect, right? It looks the perfect fit for our problem, and in fact, we are exactly doing it. I would like to stop to think for a second as what are the difficulties to do it, right? So I take an arbitrary processor like the one that we had before, that was multi-cycle and blah, and I want to do this. Am I going to find some particular problems? Stop and think for a second, right? What are the difficulties of taking an arbitrary processor, let's call it x86, and we are in the 80s, it's an 8086, is not a pipeline processor, is exactly like the processor that we had in the previous architecture, previous slide, and we want to make a pipeline. Is that going to be easy? Let's stop for a second and think. There is one fundamental difficulty, and maybe you have thought of problems with dependencies and so on. We'll get there a bit later. But there is one, in some sense, much more fundamental difficulty, which is we have this processor and we assume that it was okay that to have an extremely variable number of cycles for different instructions. The complexity of the instructions could be, in some sense, totally arbitrary. Now, if we look at this pipeline, I think we all understand immediately that what we expect, at least for this pipeline to work well, to navigate through it in a pretty regular way, right? The idea of this pipeline is that I have an instruction that is in the fetch, it should be in the decode next cycle, then in execute next cycle, then in whatever it is, this M1, it's memory 1 probably,
So, and then in memory 2, the 2 cycles after, and then in write back. Now, this contrasts hugely with our assumption before that we didn't care if instructions were of different length or complexity. Now we have an incredible potential difficulty in squeezing all the instructions into this pipeline that is the same for everyone. Now, this is something that maybe many of bachelor courses will have not stressed enough for you, but I think it's useful in this course to go back and think about this. This is what has been described as the war between the CISC and the RISC, the complex instruction set architecture computers and the reduced instruction set computers. What is this all about? It's about the fact that I have an instruction set. If I have an instruction set that has incredibly different complexity across the instructions, I will never manage to do a pipeline properly. Whereas if I have a very simple instruction set where all the instructions have more or less the same look and feel, I will be able to fetch them, decode them, execute them all in one cycle, have all of them go through some memory stages and all write back on the 6th cycle. The need of pipelining is what created the RISC processor. Still today, everybody goes around and says, oh, ARM is a RISC processor, x86 by Intel is a CISC processor. What is that? Is the fact that the instruction set lends itself well to pipelining. There is nothing good or beautiful per se in a RISC, in a reduced complexity of the instruction set. In some sense, it's even bad, right? It's very comfortable to have an instruction that my hardware will execute efficiently and which does a lot of things that I typically want. Think also of simple examples if you know them. If you don't know, I'm telling you. If you manipulate the stack, which hopefully everybody of you understands what it is, right? You have to change the stack pointer and put at the location that you have now the stack pointer a value, or when you pop from the stack pointer, so from the stack, you have to read that value and change the stack. There are two independent operations that can be done independently, but it's much more convenient to have an instruction like push and pop as you have in x86. It's not bad per se to have push and pop. It's actually much better for a programmer. Maybe it doesn't matter when you have a compiler. But again, the simplicity is not an advantage per se. The reason of RISC is that we need to squeeze everything into this framework. And this is costly. This is costly because, for instance, I think I sort of alluded to it indirectly when I was making some examples. I have every instruction that goes through execute memory 1, memory 2. So now I have an instruction that is add 2 values from the register file. I execute it, but I have nothing to do in memory. I have nothing to do in memory 2 because they are not memory operations. And then I write back. So in some sense, you could say, looking at this specific example that is completely arbitrary, but is just an example, I have taken an instruction that I could have done in 4 cycles. I fetch my add, I understand that it is an add, and I take the operand out, I do the addition, and I could next cycle do the write back and put the value in the register file. Now, instead, I have to wait 2 additional cycles in the middle to make everything evolve well. So we'll try to actually get rid of this problem a little later, because in some cases, maybe extremely bad. Suppose that you have instructions like floating point instructions that take a few cycles and ALU instructions that integer instructions that take only one cycle. How do we squeeze it easily in this framework is difficult, and RISC was born when there were no floating point units in most processors. So the point I want to make here is that essentially making a pipeline has intrinsically a cost. It's not something that comes natural for any instruction set. And even once I have an instruction set that is reasonable, most of the instructions, many of the instructions will have a latency that is even worse than just because of the pipeline, right? A few minutes ago, we said how to do a pipeline will bring additional latency. Now there is even more latency because I have to go through, for instance, in this case, M1 and M2, also for operations that have nothing to do with memory. Okay. So I have a few questions that I would like to sort of ask, reflect about this. One of the questions is, what are these registers? What is the content of these registers? We will almost never look into them into any serious detail, but I think we have to have a sense of what is in this register. So for instance, what do you think is in this register? How large you think is this register? Pause a little the video if you want to try to answer, because it's something that you probably should know, and you need to at least stop and think for a second if it is not self-evident. What has to be there is the instruction, right? I fetch the instruction, so this is the equivalent of what people tend to call the instruction register. Suppose that my instruction is in 32 bits, these are my 32 bits of the instruction with maybe little more than that. What is going to be in this register? Well, it's the result of the decoding, right? So something that will be here is that the fact that there is, I don't know, an operation to be done that is called add. Is there any information about the source register here as a field of this instruction, right? There is the information that one of the source register is R1. This information has been replaced because I indicate here that I'm reading the register file in this D phase, which doesn't have to be, but is what in many cases happens, and in many examples in textbook happens. I have replaced R1 with the value of R1. So one of the things that is in here is, I put a number at random, but is the value of R1 at the time of the decoding. What else there has to be here? And again, this is something that I would love to do interactively, because I would like you really to squeeze your brain to find out what else is in there. One thing that is easy while you think to add is the second operand, right? Whatever I'm saying for one operand is valid also for the other operand. What else? Essentially, there should be, one way of looking at it is that there should be everything that we need to operate the successive stages of the pipeline. For instance, I have to have something that says here what to do with memory. What do I have to do with memory about this operation? Suppose that it was an add, as apparently it was. Well, it's do nothing. So there is a bit that says, is it a memory operation? And in our case, maybe is a 0. Right? So there is this kind of sort of control bits, and this is why decode, right? This is called decode because it goes from a high-level description of my instruction set to something much more down to earth with all the things that need to be done. What has this guy to do? It has to write back into a register the result, right? And the result is not there, is not known yet. Actually, here there will be a register that contains the result. But what needs to be there? Well, if I have to write the result somewhere, I have to know which register is the destination of this result, right? And this information should already be here in this register. So here there will be the destination register, right? And this has essentially not done anything except going through the pipeline across the different units without doing absolutely anything, right? These two will go into my adder or my ALU here, and this one will go to control my ALU to tell what to do so that we'll have the result here. Okay, so I hope you see this, and again, if you don't, try to clarify your ideas now, because we will need to look a little bit into it when we do more complex versions of our processor. But essentially, these are we need to imagine what are the values and the content of these registers. Great. What else do I want to ask you about this architecture? Well, okay, so what are the problems of operating this kind of architecture? I'm going to help myself with a couple of animations, one where everything goes well, which gives you a little bit more detail of this, and one where things start to go wrong. So here is the little simulation that I wanted to show you. It's a bit redundant with what we have just discussed about the content of the registers and so on, but I think it's a decent example to go through. So it's a slightly different pipeline from the one we have seen before. It's actually the one that practically every book in the world uses, is the 5-stage pipeline of MIPS, and there is a little program that we see below. So how does it work? It works that at the beginning nobody's doing anything, so everything is in essentially a state of NOP, no operation, and then we fetch the first instruction. The first instruction is fetched. The content, as you see here, of the register is essentially the instruction itself, practically literally. And in the next cycle, when we start fetching the second instruction, the first instruction is presented to the decoder. The decoder sees that it is an operation that needs to do an addition and needs to register R0 and R1, so asks the register file to read. All this is combinatorial propagation, right? This is exactly my cloud, if you remember, right? My cloud of logic that is in between two registers. So during this cycle, the R0 and R1 addresses of the register file go here, the values 15 and 25 come back, and the result go here, so that at the end of the cycle, what I get here are the two values 15 and 25 that are contained, in fact, in this register. Plus, there is the addition, the information that the operation that needs to be done is an addition. And as I said before, there is the information that all these results will have to go into R2 at the end. And so every cycle things continue. You see here sub that is arrived here, our R2 that is now shown to the execution, and the execution does what it needs. That is, the 15 and the 25 enter the ALU, the plus controls the ALU to say you need to do an addition, and at the end of the cycle, this is replaced by a 40. So the two values that were here are replaced by a single value in this register. and they do absolutely nothing in the next cycle because it's not a memory operation, as I was saying before, right? So this is delaying essentially the result of this instruction to go from going to the register file, and one cycle later it will go to the register file. The only thing that is contained in this register, the only 3 elements probably that are going to be there are which register shall I write, what is the value, and whether I really have to write something in the register file, right? I suppose that you can do yourself one example of an instruction that doesn't write anything in the register file, right? Stop the video if you can't and think long enough. A store, for instance, is one of these instructions. All right, so I took care only of this instruction just to fix on one as it was going through, but you can see all the other instruction. Here there is an instruction that was a memory instruction. It was a store, is this store word. And so here there is a computation that needs to be done, which is this addition to compute the address, but there is indication that this is a memory operation. So 2 cycles later, when it will arrive here, memory understands that this is an operation. So this writing is a bit sort of illustrative, but essentially what you see in each of these stages for each of these registers are the elements that need to be there in that register for doing the appropriate operation in the next stages. Okay, all good. You can follow this simulation. You have the slides on Moodle. If everything goes well, it goes really well. It's true that we have some of the instructions that have a slightly longer latency, but if we have an instruction set that is sufficiently friendly to the idea of pipelining, and again, the x86 is and was not, but is still not, a friendly instruction set to pipelining, but if I invent a new instruction set, I will manage to potentially to have something very good. And what is very good here is that I have at the same time, right, this is time even if I didn't write it, but this means that 5 instructions are being processed at different levels on a specific cycle. So great. What is the problem that I can have with this system? There are a few problems. The perhaps most basic one and most easy to imagine is that my programs have what we call dependencies. I have, like in this case, 2 instructions where the second one says I want the R0 that I just computed in the previous instruction. The first instruction makes an addition was result goes in R0, and the next instruction uses. Why is this a problem? Well, it is a problem because I have this instruction here that is going to compute R0 based on 10 plus 1, the old value of R0 plus 1, and it will be 11, and later on it will go in the register file. And the second instruction is saying, oh, I want to subtract R0 and R1 to do something, and it's going to read R0, but of course it's going to find in R0 exactly the same value that the previous instruction was finding. So the result is that this does not work. It is semantically incorrect what we are doing. And if we want to explain what is happening, we can look at this kind of diagram, right? In the execution of the 2 instructions, we will have the value computed and available at the end of the write-back phase. At that moment, and only at that moment, it will be available in the register file to be read, but we want to read it during the decode phase of the next instruction, which is 3 cycles before. And so we have a causality problem, right? We are trying to read something that is not yet there. And this is what is happening. So this is a serious problem. And so we need to do something to address this problem. So let's go back to our pipeline and let's try to think what can we do to improve this problem. Okay, here is our pipeline. I think I said how do we improve, but it's not improve. How do we make this work? Because simply what we had does not work. There are a few ideas, and again, this is one of the places that it pains me most not to be with you discuss, because there are many different solutions, very fundamentally different. Try to think it for a second and make a little pause. Try to think of more than one solution maybe, because maybe you are thinking of one of the solutions that we are going to look at, but it's good to discuss several different solutions. And in fact, we will, along this course, come back to some of these solutions. So let's do a little bit of a pause. Okay, so probably the solution that you thought first of is the classic solution that one presents in front of this of this kind of pipeline, which is to say, I have to stall. I cannot continue. If I have an instruction that is in the decode stage and is reading the register file and is going to find a wrong value in the register file, I should stop it, right? I should prevent it from getting this value from the register file and hold it there until what comes from the register file is correct. So how is that going to work? We need to modify a little our circuit for this. We need to detect that there is a problem, right? And again, let me repeat what is the problem. The problem is that I have here a register. In our example before, it was R0, that I want to read because this is what I am going to send to the register file. And there is a previous instruction that is going to write a new value to R0, which therefore is the value that I want, as opposed to the value that is already in this moment in the register file. So this is what I need to detect, right? How do I do it? Well, I know where these instructions are going to write, because as I told before, I have here one field that is the destination register. And it is true for all these instructions, because it's only here that I'm going to use this information. So here there is written something that says this instruction is going to write in R0, this instruction is going to write in R2, this instruction is going to write in R3, and whatever else. Actually, maybe this is going to write in R0. So there are two values of R0 that are being computed. So what shall I do? Detecting that we have this problem is relatively easy, right? And what I need to do is to say, if this and these are equal, or this and these are equal, or this and these are equal, and so on and so forth. Don't let me draw everything. If any of these three are equal, of these four are equal, I have a problem, right? So I need a OR gate here. And this is my stall signal, what says, don't advance the instruction that is being decoded in this moment. Is this enough? It is not, right? It is not, but for a trivial reason, is that there is here a second operand, and so everything that I've done for one operand, I should do for the second, right? So I need to also compare this with this, with this, with this. I hope you understand what I mean. And there are actually 8 values entering this. So if any of these combinations has a problem, I need to store. Okay, this is half of my work, right? I have detected, and it's actually pretty easy for me to detect, that there is a problem. Now, this stall signal I need to use to stop this instruction from advancing. So let me delete what I've done. Now I have computed, I have created the signal that says to stall. Now, how do I use this signal stall to prevent the instruction that is here from advancing? So the first thing that I need to do is that I need not to change the instruction that is here, this cycle, right? So I need to basically put an enable in this flip-flop and stall the signal that I generated before should not enable this flip-flop, so that this flip-flop refuses to take the next instruction and keeps the same instruction there, which is good because the next cycle, again, I will have R0 here, and I will try to read again from the register file and see what happens, right? So this is good, I freeze. What else? There is another problem, is that now I just fetched an instruction, and this instruction is coming here in the register, but I'm refusing to take it. So this instruction is lost somehow. So I need to get this instruction again. So the simplest way that I can do this is that inside here, it's not visible explicitly in my figure, but is inside the fetch unit, there is a program counter, right? The program counter is the one that gives the address to the instruction memory to read the next instruction. And this PC typically increments by whatever value it should, maybe 4, depends on the architecture, to go to the new value of the PC. And what I need to do is to prevent it. PC is a register, so also as an enable, and also this one I need to disable, right? I need to have the PC that doesn't take this value PC plus 4, but keeps the same PC, so that again will fetch a second time from the memory the same value. Okay, so then I managed to freeze this part, I'm freezing this part. What else do I need to do? Well, I need to avoid that in this stage of pipeline, this decoded instruction goes this instruction, right? Because I have this R0, I read the R0 that is wrong, and I'm putting it here. If I let this, register do its sort of normal job, it will take this as a good instruction and take it over. So what I need to do is maybe something like this. Conceptually, have a multiplexer here that replaces the instruction that comes from this decoding that is not going to happen well, replace it with an instruction that is a no, right? So essentially on stall, I should take the NOP instead of taking the normal instruction. Now, of course, I'm probably not going to implement it like this. There will be something here in the instruction that is a valid bit, and I will put it to 0 to mean whatever there is there is crap, just don't look at it. But conceptually, it's exactly the same thing. Okay, are we clear? Is this kind of circuit, I hope, something that you have seen to some level of detail? I think it's almost correct what we have done. There may be little problems in some little details, but essentially this is it, right? So I compute the fact that this effect is happening, and I stop a part of my pipeline, the initial part of my pipeline, while the problem is there. Notice I deleted the part of the drawing that we had that I had before. You can go back a little bit in the video if you want to see it, but it's easy to convince yourself that actually this solves the problem for good in the following sense. I had the R0 here that was detecting the problem with the R0 here. Now I'm letting this one advance through this, and then R0 will be here next cycle, and replace this with an op. And next cycle, the R0 will be here, and so on and so forth. All throughout this time, I will detect the conflict with the R0, because you remember I was checking at all the stages of the pipeline for an R0, so I will continue to see R0 here, then here, then here, then here, and only when this guy is finally writing it in the register file, there will be no R0 anymore here, and finally my instruction will de-stall, it start advancing again. So all good, right? All this is working perfectly well. We have somehow solved our problem, except that I don't manage to have this work. Okay, I manage. Very good. The problem is solved. What is the impact of this solution? The impact of this solution is that my pipeline is not working as well as it was working before, right? Now I have my instruction on which I have this dependency that is executing in 5 cycles. I have the second instruction that has the dependency that does nothing until after this one has finished. This is the decode, this is the fetch, and only here I do the fetch of the next one, and so on and so forth if everything goes well. But what has happened here is that I have here the lost time, and I lost time for every instruction also that follows, right? So essentially, if I had the dependencies all the time, I would have practically no advantage in having a pipeline. So I have a pipeline only to the extent this doesn't happen too much. All right, again, fine, we understand, we can perhaps live with that. Anything else that creates a problem in doing pipelines? This one is solved, we have done the right thing. Are there other problems? So I'm not going to enter the details here in this video, but there is also the control dependency. What we have just seen are the data dependencies, the fact that the one instruction depend on the previous one. There are also control hazards, that is the fact that there are branches, and the moment a branch enters our pipeline, I decode it and start execute, like I do a comparison that is essential for me to know if I have to change the next instruction, the next instruction to be executed or not. And by the time I am there to make this decision, I actually have already fetched 1 and 2 successive instructions, right? And so I have the same causality problem in the case of control dependencies, that is, in the case of branches. It's exactly the same problem, right? I mean, it takes a different form, but it's exactly the same causality problem. And it has to be essentially handled, it can be handled in similar ways. dependencies. We'll come back to this control a little bit later, but please go and maybe revise what are the typical solutions for the control dependency. What I'm interested in here, so essentially now we have solved the simple pipelining, right? Provided that we do the appropriate things for control hazard, for control dependencies, provided that we do what we have almost completely done for data hazards, provided the fact that we have a good instruction set that is lend itself well to a pipeline, we have a pipeline and somehow we are ahead. Before we advance, I want to come back to one thing that I said, now you forgot already because it was maybe 15 minutes ago, but I said there are many solutions to the problem of the data dependencies, right? And let's rewind for a minute, right? And we said, okay, great, we do the pipeline, and then we said, oh my God, there can be dependencies. What do I do for the dependencies, right? And the data dependencies. And we found this solution, which is to stall the pipeline. I want to go back to that point, and once more, it would be much better to do this in presence, but I want you to really think and stop and say, is there some other way I could have gone? Could have I spared all these additional circuitry that we have been drawing on the slide in the last 15 minutes and do something completely else to solve the problem of this semantic mistake that my pipeline does, that doesn't use the R0 that I want to use. Think of it for a moment. Take a pause and think, what else could you do? Completely different. So what is this completely different way to go about this? I have this pipeline. I have made my sort of, call it naive pipeline without noticing that there is this problem that dependent instructions don't get executed properly. What could I do else to make the system work? And the dramatic idea that one could have, dramatic because it's very much different, is to say, okay, it's a fact of life. If I have two instructions that follow each other, if I have my add R0 something something and sub from R0 and some other thing to go into another register. So if I have this dependency, if I have these instructions, one following the other, this R0 will not be the correct R0 because of the structure of the pipeline. Let's live with this. Let's accept this as a fact of life. So what shall I do as a programmer if I want to get these things to work? Let's take a page and let's think for a second. So if I wanted that this R0 is indeed the R0 generated by instruction 1, what shall I do? I should wait long enough for the instruction to go through the pipeline. And I need to wait 3 more cycles if I'm counting correctly. If I'm not counting correctly, it doesn't matter, but I need to figure out how many cycles I need to wait before I get. So if I write the code in a different way, like this, I obtain the functionality that I had, but I did not change at all the hardware. Okay, so this is the interesting part, right? Now we can do 2 things, right? Either add exactly these knobs. Remember what I put with a multiplexer, which is a sort of a funny way to represent this in hardware, but it's not wrong. where I had this multiplexer that inserted a knob, it was dynamically, during the execution, looking at, oh my God, there is a dependency. Let's insert a knob, and inserted a few times until this value will go back into the register file. And now what I'm saying is, my hardware does this. It's up to the programmer to insert the appropriate number of knobs. There is no way that you can read this R0 before 4 instructions. There is a latency in this operation that is of 4 instructions, and only 4 instructions later you can read the R0. So if you are not happy with, if you want to do it immediately, put 3 knobs in between. Is this a silly idea? It's not that silly, right? First of all, is this worse or better than what we were doing before in terms of performance? And think about it for a second, right? At best, it is the same, right? Because if I am told the right number of knobs that I have to put, I'm putting exactly the same number of knobs so that the hardware was adding on the fly, right? So in terms of performance, there is absolutely no difference. Or is there? Actually, there is a difference. Is that now that I am telling all these things to my programmer, I can say, okay, here there is a mul. Suppose that this is an R1. Now there is an instruction here that has nothing to do with the 2 previous instructions, has nothing to do with this R0. So why don't I put this instruction here in place of one of the knobs? It does the same purpose, right? It serves the same purpose. It creates distance between the add and the sub. But I'm doing something useful. So this idea of telling the programmer of all these problems in the pipeline and letting the programmer take care of this, of course, puts a burden on the programmer, but potentially could do better in performance, because I could maybe find 3 instructions that can go in place of these 3 knobs, and now I don't lose anything, where in the architecture that we have seen before with our computation of the stall and so on, these 3 cycles are completely lost. Here, there is no problem. I can fill them up. Is there a disadvantage in doing what this sort of second version of things? Is it much, much worse in some respect? And yes, it is much worse in one respect. Maybe it's very trivial and you didn't even think of it, but it's because it's so trivial, is that my original code that I had for my machine, the first processor that we discussed today, the one completely sequential, that code does not work here, right? As we said before, my code, which has the add and sub adjacent, is wrong, has a different meaning here. I really need to go in my program and put at least the NOPs, the knobs, or something else. What that means is that there is no, the expression is binary compatibility. If I take a program from one version of my processor, the sequential one, the multi-cycle one, to this pipeline version, it doesn't work anymore. I need to recompile, I need to recompute the proper sequence of instructions. They are always the same instructions actually, but I need to reorder them or space them with knobs appropriately. These two ways of solving the problem are going to be a sort of leitmotif of this course. They will come back in this course in very different places. The fundamental choice here is between I decide what the schedule of execution of my program is in real time during execution. It's what we've done when we started adding here all this logic that was detecting the problem at the last nanosecond, right? When it is happening, oh my God, there is a problem. Let's solve it by doing something that makes the semantic behavior proper, as opposed to saying, I will not do anything in my processor and in my hardware. Let's decide beforehand and before we start to execute anything, something that will work. This we will call the first dynamic scheduling. I hope you understand the term, right? We are scheduling, we are deciding when things get executed, but we do it while they happen. And static scheduling, we do it at the moment of compilation or at the time of programming if you are really programming in assembly, but typically it will be the compiler that takes care. Everything that we continue to do today and next week and the week after will be in this dynamic world, where we will do the hardware to do the right thing irrespective of what happens. And then we will come back to revisit all this in a fundamentally different way by saying, I want an hardware that is incredibly simple, and I will push all the job to make it work well on the compiler. I will do a compiler that is probably much more difficult to do, and we'll see how much more difficult it is. But my hardware will be simple. Okay? Very good. So now we have this pipeline, and we have this pipeline that works, and let's forget the second way that I just said. As I mentioned, I will come back to this a bit later in a few weeks. For now, we go for fixing the hardware, not fixing the code, okay? So we have added in this processor all our logic to store the pipeline, and we start wondering whether we can do any better than this. Is there something better than we can do? What we can do to improve the situation is probably best seen by going back to one of these slides of my bachelor course that once more are available in Moodle, so you can go back there for reference. To improve things, we can observe the following. This is the situation that we have, right, with this causality violation. So this is what doesn't work and cannot work. But if we look a bit carefully to this timing diagram, what we notice also is that at the end of the execution phase, so at a specific moment in time, in this register, I have the result. So I have the value that will go in 2 cycles in R0. But this is also the last moment when I need to have the value to start computing over it, to execute for the sub. So in a sense, is what you see with these 2 points, right? I have the data just in time, they are just computed the add, and I am ready to compute the sub. So I'm not violating the causality, except that I have the value in the wrong place. The value is not in the register file where I'm looking for it the cycle before, the value is in the register just after the execution. So the idea is that I can add a path to my pipeline that starts to become messy and not be a nice pipeline as my intuitive pipeline of 1 hour ago. But that solves the problem. That forwards or bypasses the register file and brings the value in the right place. And so if I do this, actually I have, in this very specific case, a perfect advantage in the sense that I don't lose any cycle because, again, it's there. Now, I want to ask you questions about that, right? For instance, what if the first operation was a load instead of an add I? That is an operation that has the value that is actually available only at the end of the memory cycle. So let me come a little bit back here in the animation, and let's try to modify this example so that this is not an add, but is a load word, for instance. So the real value of this operation is going to be available at the end of the memory cycle here, but on this cycle. And when I need the operand is still here. That is one cycle before. So notice that even if I put here a path like this, it will help because I will use the value on this cycle as opposed to use it on this cycle when it is in the register file. But I will still need to shift this part of my execution, these three parts, one cycle later. Or if I want to draw a little bit clearer, right, I should have nothing, sorry, you don't like me. I should have here the execution, here the memory cycle, and here the write back. Okay, I hope once more that these things, I'm going very fast because I assume that you understand these things. If you do not, because it's not very clear, continue perhaps looking at the at these slides from the bachelor course, or go and see the textbook by N.C. Patterson, because it will help you understand these aspects. So if we go back to our pipeline, we can add plenty of these forwarding paths, or these paths to get into execution any of the pending results that are not yet in the register file, and bypass the register file and bring these values to the execution unit. Maybe one question that I like to ask you as a sort of, again, revision exercise is how complicated it is to control this, right? What I'm doing here is a bit, in a sense, bizarre, because I'm showing here just plenty of inputs, but in reality here there will be a multiplexer that will be choosing which input to use, and the question is, how do I control this multiplexer, right? I hope the question doesn't seem to you too horrible to handle, but we can try to handle it together. Let's take care of, for instance, this choice, right? The choice between the normal one and the execution to execution forwarding path. So let me ignore the existence of these two. So I have here a multiplexer, and I need to control this multiplexer to select either this or this input. So how do I do that? How can I do that? Well, this depends again from the dependency, right? If there is a dependency, if this destination R0 is, which corresponds to the value that I have in this register, is the same thing as the operand that this instruction wants, right? So you see, it's the same logic that we were doing before, right? If this and these are identical, essentially what I want is to replace the value from this register with the value, sorry, I just did a mistake in drawing. It's okay to be a bit imprecise, but this is too much. The value from this register with the value from this other register, right? Is the principle clear? There are a little defects on the implementation that I'm going to correct in a minute, but I hope the basic idea is clear, right? If there is a dependency, wherever there is this dependency, and how do I find the dependency is the same thing that I was doing before. When I find the dependency, if there is this dependency, I just replace the value that has been fetched by the decoder from the register file, which is wrong. I replace it with the good one from where it comes. So what is the problem that is there? I want to give you the time to find it out. There is something that is maybe not wrong, but a little odd, at least here. What is it? Well, it's the following, right? It's the fact that here I had R0, I said before, and again, I'm saying R0 because I'm thinking of my example before, and during the execution, R0 has become the value 345, whatever it is, that comes from register 0. And now here, I am pretending that I can read here R0 to compare with this. But normally, I would not have carried R0 from this stage to this stage. Normally, this stage doesn't need to know that the source of this from the register file was R0. Okay, it's a detail, right? It's a detail for two reasons, because there are two solutions to this. The first, super easy to do, maybe not the best one, is despite the fact that I don't need R0 anymore in this part of the pipeline, now I do need it at this stage of the pipeline, so I put the register there and I keep this information there so that I can find it. And this is one possibility. And the other possibility, sort of equally cosmetic, is that whatever I'm detecting between this, let me change color maybe, between this and this on this stage, I could have detected one cycle before. I would have computed this, and now I would have put this into the register file and into the, into the pipeline register and then control. Okay? If you are not totally clear about the blue modification and the violet modification, maybe you can ask me or you can try to understand it with the book. It's just a very little problem of timing. The basic concept on how to control this part is what was drawn in red before. Very good. So let me clear this, except that I always have this problem. I will get more skilled with this as the semester advances, but anyway. All right, so this is the little trip that we have done today, right? We started with a processor that is the simplest. We have been going through a number of completely basic concepts on how do we do circuits in CMOS, how do we consume energy and so on, which I think are useful to bring back to memory what is critical path and these kind of things. But while doing this, we have reconstructed the very basic starting point of a pipeline processor with a number of improvements, these forwarding power. The question is where we go from this, and this is where this course really starts. So I hope this course was useful for you for doing one of two things. Remember those things that you sort of knew but have somehow a little bit forgotten. If they are too much forgotten, please take the time to go and read the book or read any source or see the slides of the basic course in Moodle to make sure that you are up to speed next time, because we will try to go a little bit faster, or at least we will build on the things that we have seen today. If you have never seen the things that we have been discussing today, these are considered prerequisite for this course. So if they are completely extraneous to you, maybe think whether this course is appropriate for you, or send me an email and maybe we'll try to talk on Zoom to try to understand how you can catch up, because it's important that you catch up these things as quickly as possible, because again, otherwise you may not understand the rest. Okay, thank you very much for your attention. I wish you a great week, and we will see each other with another episode of this course.